Welcome to Lecture 5 in the series on special relativity, electrodynamics, and general relativity. We're up to the beginnings of a discussion of relativistic dynamics, first steps. So this is a lecture which will consist of several parts in which we'll try to invent dynamics which will be consistent with the postulates number 1 and number 2 of Einstein's world. Okay, we'll begin with a review of Newton's dynamics, and then we'll see what the problems are there, and then we'll move on to Einstein's dynamics and try to develop his concepts of energy, momentum, and mass, which will replace Newton's ideas, which will be inconsistent with the existence of a speed limit that's essential in special relativity. So remember, in Newton's world that F is equal to the time rate of change in momentum, and the momentum is mass times velocity. If we have two bodies that are interacting, okay, that then their interactions, their forces satisfy Newton's third law, okay, and so the time rate of change of the total momentum is the sum of the two forces. The forces satisfy action-reaction, so they sum to 0. And the total time rate of change of the momentum is equal to 0. Okay, that's as promised that the concept of action-reaction in Newton's world is essential to momentum conservation, of course, which is essential to his development in the Principia Mathematica of an understanding of the motion of the planets. And just about every application that we have, this is critical. We'll have to have, in Einstein's world, a replacement of these ideas, because momentum conservation, energy conservation are essential ingredients in the physical world. So in Newton's world, then, the time rate of change of the total momentum of the two particles is equal to 0. Okay, and so the total momentum is a constant. It's convenient to rewrite that in configuration space, in real Euclidean space. So if I define the position here of the center of mass as the weighted average of x1 and x2, I see that taking the time derivative of it gives me upstairs just the sum of the two momenta. Okay, I learned that the time rate of change of the position of the center mass is equal to a constant. Okay? So, for example, if I'm in the center of mass frame, okay, then that's by definition where the sum of the momenta is equal to 0. In that case, the time rate of change of r, I write a dot here to indicate d by dt, that's done in the textbook, that the time rate of change of r is equal to 0. Okay, the momentum sums to a constant, which is 0 in the center of mass. So if I choose the position of the center of mass to be the origin of my coordinate system, it stays there. The two particles move about, maybe they orbit one another, and the center of mass stays put. Okay. So that's how the conservation laws work in Newton's world. We've also discussed how these conservation laws behave under Galilean transformations. Remember, in Newton's world, all inertial frames are equivalent and they're related by Galilean transformations. And we already checked that if we have momentum conservation in one inertial frame, the Galilean transformations preserve it, and we have momentum conservation in all frames. That's essential to understanding Newtonian mechanics. We want to have the same concept to be true in Einstein's world, because in Einstein's world we still have postulate 1, that all inertial frames are equivalent. So if we have momentum conservation in one frame in Einstein's world, it has to be true in all frames. But then we have to ask, what replaces these statements in relativity? In Einstein's world, the energy and mass are going to be unified, and this simple definition of momentum, for example, is not going to generalize. We have to come to grips with what's the formula for momentum in Einstein's world that will be consistent with the existence of a speed limit. What's the formula for the energy in Einstein's world that will be consistent with the speed limit. Those are the things that we want to discuss today, and we're going to discuss them through a Gedunken experiment. This is our first shot at the concepts. Let's do it in a concrete case of a little experiment that we can imagine doing in the lab. Later we'll approach the same ideas from a more fundamental perspective that will give us the general ideas and will give us a formalism to apply these ideas in other problems which we can only imagine at this point. So we begin with a famous Gedunken experiment. Okay, we imagine that we have a box, and one end of the box we have light rays shooting out to the other side. Okay, and we're just going to use momentum conservation to try to understand the behavior of the box and the light in these circumstances. There's one thing I have to steal, and that's a property of light. We have to steal the fact that we'll discuss and derive later that light carries energy, and the energy it carries is related to the momentum it carries by E equals P times C, where C is the velocity of light. This will be derived, so we'll fill in this step later, but I need this right now. Okay, because I'm going to apply momentum conservation to see how the box responds when light goes from one end of the box and gets absorbed at the other end of the box. Okay, so that's what happens in these pictures, showing the time sequence of events. In the first picture, light leaves one end of the box, and then it travels a distance L, and arrives at the other end of the box, and that's shown here. Well, when the light leaves this end of the box, of course the box will recoil. Light carries momentum in this direction, so the box will recoil in the opposite direction. So throughout the duration that it takes light to reach from this end to this end, that's a time L over C, the box will be recoiling, and it will only stop when the light hits this other end and deposits that energy back on the box. So it's a very trivial little example, but it brings up some matters of principle which we'll want to expand upon. So light carries this energy, and so the box, I call it of mass m, where m is very large. Okay, m is going to be so large that we can do the kinematics of the box by Newtonian rules. Okay, that's approximately true, and it's good enough to get us the answer to this problem. In the problem sets of the textbook, you'll redo this problem exactly and get the same answers. Okay, but I'm going to take the spirit of that was presented in Einstein's first derivation of this and carry it through. Okay, so the box of mass m recoils. That means it moves to the left. The light carries a momentum p to the right. The box therefore recoils to the left. Action reaction. And it does so with a velocity that's just the momentum over the mass of the box. Okay, the momentum is related by the energy carried by the light as E over C, and so here's the velocity of the box that it has in the interim while the light is traveling from one end to the other end. Light reaches the end of the box at approximately the time L over C, just distance divided by speed. Okay, and the box therefore moves to the left by a distance, which is just velocity times delta t. Putting in the delta t as L over C. Putting in velocity as minus E over mc. The minus meaning that it's moving to the left. I see that the box itself moves by that amount. So it looks like the center of mass of the system is moved. That's a clear violation of the laws of the real world. Okay, you don't get something for nothing. Okay, that's crazy. The center of mass can't move. Okay, if that were the case, we can make a perpetual motion machine. Okay, so we conclude that something is missing here. Okay, the center of mass can't really move. So when E goes from one end to the other end, it must carry some mass from one end to the other. That was Einstein's insight. So conclude, light must transfer mass m from one end to the other so that the change of position of the center of mass is 0. Okay, so let's calculate the position of the center of the mass after this experiment has been done. Well, let's call little m the mass that light of energy E carries from one end to the other. So it ends up on over here, okay, a distance L to the right. So that contributes a positive term to the change in the position of the center of mass, ml. And then the box recoils and it moves to the left, okay? And its position of the center of mass is its mass times its change in position, like that. And my condition to calculate little m is that this equals 0. So little m is cooked up in such a way that the center of mass doesn't move. Okay, so we're patching up an error here, and maybe we'll discover something interesting in doing this patch up. And I assure you we will. Okay, so little m is given by this equation. I know what delta x is. I just calculated that over here. Okay, so I put that into the formula for little m, and lo and behold, I do my little algebra, check me, and I see that little m is equal to the energy carried by light divided by c squared. So, solving for E, I get the most famous equation in physics. E is equal to mc squared. Okay, light carries the energy E, and that energy has a mass equivalent given by E divided by c squared. Okay, it's a tiny, tiny number. In the problem sets, I'll ask you to put in numbers into the problem, okay, and you'll see it's really extraordinarily small, but it's non-zero and it's absolutely essential. So we learned from this little example, okay, that we'll have momentum conservation, we'll have energy conservation, and we'll have a conventional ideas about the motion of the body, but we have to have that mass and energy are different manifestations of the same concept. Okay, so in relativity we learned that mass can be converted to energy and vice versa, right? The energy was carried by light, but it shows up as mass when the light is absorbed at one end of the box, and we can imagine going the opposite way. Okay, so it's a big change from Newton's world, where in two-body elastic collisions, the mass of each body is conserved, and the total momentum is conserved. So now, if we're going to think about collisions in Einstein's world, we have to find out the new rules, and we already know that one of the rules is that mass is not going to be immutable. Mass and energy are going to be aspects of a similar concept. Okay, so to find out what the formula is for momentum, what the formula is for relativistic energy, let's consider a very simple collision and require that collision, that the energy and the momentum in that collision satisfy covariance. That is, it leads to energy and momentum conservation in any frame if it's true in one frame. So in this illustration, we use the little bit that we know about relativistic kinematics. It'll be the quote addition formula for velocities, and we'll use that to determine the correct formula for the relativistic momentum in Einstein's world. That's the object of this exercise. We'll also get a formula for the relativistic energy, and in that formula we'll see that E equals mc squared is a special case of a more general formulation. So that's where we're heading in this funny little experiment. And the fun little experiment is the easiest collision I can imagine. It's the collision that's totally inelastic, okay? And we want to just analyze it. So here it is, two-body collision, and we'll describe it in Newton's world first. So I have a target particle here of a mass m, and I have a beam particle of the same mass that's heading toward it with a velocity u. That's the situation before. And then the situation after is totally inelastic, so the two bodies stick to one another. Perhaps they're putty. Okay? And then the body will move to the right at a velocity u bar, which I have to discover. Okay? And it'll be determined by momentum conservation. Okay, so let's take a look at it. So I write down momentum conservation. Mu plus 0 is twice m, the two masses, times u bar. And I see I can calculate for u bar, and it's just half u. And I think this is a common little experiment that you've done in the lab, okay, that the composite particle has half the velocity of the initial beam. It's an inelastic collision, so there's some kinetic energy which is lost. Energy is conserved, but some kinetic energy is converted to heat, and we can figure out what that is. The conversion to heat, I'm calling it Q, should be the kinetic energy before minus the kinetic energy after. How much kinetic energy is lost? Well, the kinetic energy before, in the initial state, is one body of mass m going with velocity u, so that's a half mu squared. And at the end, I have the composite particle moving with velocity u bar. And so I put that in here, okay? And I calculate that Q is a quarter mu squared. Also notice that it's also mu bar squared, okay? Just by doing the arithmetic. You see that over here, okay? That a quarter mu squared is also equal to mu bar squared, because u bar is a half u, and so I can write that out. Maybe I'll write that out on the poster, because later when we do this problem with the rules of Einstein, we'll want to pick that up. So this is mu bar squared. Okay. So okay, so that's fine. That's how the inelastic collision looks in Newton's world. And let's try to generalize this to relativity. Okay, we're going to do this, and our object is to find out what's the formula for the momentum in relativity, so that this description is covariant, is equivalent in any reference frame. So let's write down the form of the equation for the momentum. The momentum formula must be found, and the momentum will have this form. It's going to be p. Well, it has to be proportional to the velocity. That's the only vector in the problem. It has to be proportional to the mass to get the dimensions right, and then it can be then what we don't know is then absorbed into a function which is a dimensionless function of dimensionless variables. What are those variables in the problem? Well, this particle here has a velocity u, okay, and relativity comes with a velocity, the speed of light. So f will have to be, it has to be a dimensionless variable, because p has the right dimensions of m times u. So f is dimensionless, has to be made out of dimensionless variables, and the only one that I have at my disposal is u over c. Okay, so that's just parameterizing it. Okay, I just name things really, and I've used some dimensional analysis to make progress at this point. That's all I've done, and I take this product of f times m, and I call that the relativistic mass m of u. I'm just using a shorthand here, and I'll just use this notation for the purposes of this problem, and I'm not going to continue it later in the course. Okay, so that's my momentum. So in order to have momentum conservation in this problem, you see, it would say that the momentum before, that's m of u times u, right, we're using this formula, is equal to capital M of u bar times u bar. Okay, so I have several things to do here. I want to find u as a function of u bar. I'm going to do that by using a transformation to another frame. And then I want to find m of u bar as a function of u, get an explicit formula for it. Those are the chores I have to do, and once I've done that, then I'll know my momentum. I'll know my function f, and I'll be done. Okay. our equations must be covariant. So let's use that fact, and instead of viewing it in this frame, which we've already used that information to acquire this formula, let's look at the rest frame of the beam. Okay, so let's just take a look at this and conserve momentum in the frame in which we turn things around. Okay, so we go to the rest frame of the beam. In other words, we do a boost by the velocity u in the direction against the beam. Okay, so now the process looks like the beam is at rest, the target is coming at us, and we've turned around the final state. Okay. Okay, so that's the situation here. Clearly, the initial state is turned around. Okay, and so the final state will be turned around. Okay, S prime that defines this new frame is moving to the left with a velocity of minus u in order to bring the beam particle to rest. You see that? Beam particle to rest. But what does it do? So I understand what it does to the beam particle and the target particle. That's obvious. But now, what does it do to the velocity of the composite particle afterwards? Well, the composite particle afterwards has to end up with a velocity minus u bar, because it just turns the picture around. And that must be obtained by boosting u bar to the left by a velocity u. Well, that's one of the very few things I know how to do. I know how to add velocities in relativity. I know the formula for that. And so I write down that formula. Minus u bar must be the result of adding u bar to minus u. So it's linear upstairs, and then there's that denominator downstairs that we had last time, and that's the critical element. So I'm just stealing from our previous lecture the relativistic equation for adding velocities, and I'm applying it to this case. So now I'm bringing into the problem some relativity. Okay, this is really the first place that I've done that. And then I can take this formula, do a little algebra, and solve for u as a function of u bar. And there's the result. I can check that that I haven't made a mistake, because I can take the non-relativistic limit where both u and u bar are very small compared to the speed limit, and I see in that case that u bar is approximately a half u. Remember from the solution of Newton's problem, that's the exact answer in Newton's world. So my relativistic formula reduces to that in the appropriate limit, but then it has this nonlinearity downstairs, which is of course critical to enforcing postulate 2 of relativity, that there's a speed limit. So we'll keep that around. So make a note of that formula. We'll be using it later on. Make a note of this formula, momentum conservation, in the lab frame. So we'll come back to them. Okay. So the next thing I want to do is to look at the collision in another frame. In this frame, I'm going to make a boost in the minus transverse direction, the y direction, by a tiny velocity v. At the end of the calculation, I'm going to let v go to 0. But for the moment, let's just imagine that v is very, very small. Okay, well then I have to, in addition to conserving momentum in the direction of the beam, I have to conserve momentum transverse to the beam. So I'll write down momentum conservation transverse to the beam. And that's right here. So m u prime v plus m of v times v is equal to capital M of u bar prime times v. Right? All of the particles have a common velocity transverse to the beam, because they get that velocity just because I'm in a frame which is moving transverse to the beam. Now the velocities that the particles have is changed a little bit because in addition to having the velocity in the beam direction, they have a tiny velocity in the transverse direction. So that's why I put these primes in here. Okay, and in one particular case, this is the momentum of the beam particle. It was at rest in the original frame, and so when I boost to a frame of velocity v in the minus direction, it has a velocity v, and so it becomes m of v. Okay, and then these other m's have arguments which are adjusted for the non-zero velocity. But I'm not so concerned about that. The details for the general case are written here on the sheet, but who cares? I don't need it, because I'm going to only be interested in the case v goes to 0. But anyway, this is the momentum conservation now in the transverse direction. All terms are proportional to v, so I can slash away, cancel out v, and get that the masses initially of the appropriate velocities add up to the final mass there. Let's take the case in that v goes to 0. Then I have that the masses in the lab frame, the relativistic masses, add up like this. So I have a new conservation law. The relativistic masses are conserved by doing this. I end up with v goes to 0, and so these arguments here are the arguments that I had for the lab frame. Okay, I took v different from 0 just to get at the velocity transverse to the beam, and then I take it to 0, and I get the statement that relativistic energy is conserved. So it's a little trick, cute trick, and okay, and we'll be using it. You see how critical it is now, because now I have two equations. Okay, I have the original equation for momentum conservation along the beam direction, but now I have an equation I can get rid of capital M of u bar, the mass of the composite particle. I put that in here. Okay, and then I can solve for m of u in terms of m of 0 just by doing the arithmetic here. You see it? You see that arithmetic? Just do it. Okay, and so this determines then the velocity dependence of the relativistic mass. Okay, m of u is m of 0. That's the rest mass of the beam particle times u bar divided by u minus u bar, as you see from the factors of u and u bar in this formula. Just do the arithmetic. And remember, u and u bar are in the x direction, so I don't really need the vector signs there. Okay, and now on the previous sheet we had the equation for u bar in terms of u given by addition of velocities. So I can do a little bit of arithmetic and get rid of u bar here and here in favor of u. And I do that, and I get a very cute result. And I want you to check my arithmetic. It's also written down in the textbook. That this term in parentheses is nothing but gamma of u. Okay, that is, it's equal to 1. You just do the arithmetic. Okay, nothing. We're not going back and pulling any result out of the hat or anything like that. Just do the arithmetic, and you'll get that it's 1 over the square root of 1 minus u squared over c squared, a gamma factor that we're so familiar with from Lorentz transformations, okay, from boosting from one frame to the other. So in summary, and this is the result we wanted, we see that m of u, the relativistic mass, is equal to gamma times m of u, where gamma is evaluated at the velocity of the particle in the lab. So that gives us then our formula for the relativistic momentum. If we want to have momentum conservation, and we want that formula for momentum conservation to be covariant, that is true in any frame, any inertial frame, then P has got to be gamma of u times m of u. Okay, that's our result. We have a little more work to do, but that's the major result that we're going to be using again and again. We're going to derive it in a more general form, but we've got it now for the first time. Okay, and you can sort of see how it gets some relativity in it. If u is very small compared to c, then gamma goes to 1, and we're back to Newtonian formulas. P is equal to m, rest mass, times the velocity. But now imagine that u heads off to c, gets close to c, then gamma goes to infinity. So you see it enforces the speed limit. Okay, as you approach the speed limit, the momentum goes off to infinity, and so you can always approach it, but you can't reach it. And so P has that information in it. It's an interesting formula. Okay. Now let's get the relativistic energy. So I have a little more work to do, okay, to get the formula for the relativistic energy, and to do that, I'll just play my game again of viewing the collision in another frame. I'll choose to go to the center of mass frame. Okay, so I'll boost to a frame in which the beam and the target come at each other with a common velocity. Okay, and of course that common velocity has got to be u bar, so that the final composite particle is at rest. Okay, right? And so I'll just be boosting to this particular situation. Okay, so that's my center of mass frame, and just like we derived before in the lab frame, we could consider the frame in which there's a transverse velocity v, and conclude that the relativistic mass of him, okay, plus the relativistic mass of him, of the beam, is equal to the relativistic mass of the final composite particle. Like here, I just reminded you of what the statement was in the lab frame. Now I make the same observation in the center of mass frame, and so I get the same kind of relationship, except the arguments are different to reflect the new frame. Okay. But this is a nice handy formula, because I know m of u bar. Okay, that's given by m of u is equal to gamma m of 0, rest mass. So here I have to add m of u bar plus m of minus u bar. But of course, the mass doesn't depend on which direction the particle is moving. It only depends on the speed, not the velocity. So m of minus u bar is the same as m of u bar. And so I read off that the composite mass is equal to twice m of u bar, where this is a little m. And I know from what I've done up here that little m is equal to gamma times rest mass. And so I have a formula now for the composite mass. It's just twice gamma of u bar times m. Okay, right. So that's what I wanted. Okay, that tells me what relativistic how relativistic mass depends upon velocity, and I can look at that formula and play around with it a little bit. Remember, in Newton's world, masses just add, and capital M is equal to twice little m. Okay, the mass of the composite particles just add the masses of the two particles and make it up. But that's not true in relativity. There's a gamma factor that accounts for the velocity of the particles. However, if u bar over c squared is much less than 1, then I should return back to Newton's equations, and I do that because when this is the case, when this inequality is the case, I can take the formula for gamma and Taylor expand it, okay, and it becomes 1 plus a half u bar squared over c squared. And so I see that capital M reduces in that case to twice m the mass of the beam plus the mass of the target plus m u bar squared over c squared plus higher order corrections. Aha, m u bar squared. I remember in Newton's case that was exactly the heat generated. Okay, so let's use that definition and write down the exact formula in the case of relativity as capital M is twice m plus q over c squared, right? This is q essentially over c squared, but now I'm incorporating in q all of the dots, the corrections coming from relativity, okay? And I identify the difference between the composite mass afterwards and the two masses before as what's lost to heat. Okay, I call that Q. So I see in this formula that Q over C squared is the mass deficit, capital M minus 2M, that's delta M. And so I see that the heat that's generated is delta M times C squared. Okay, So here's a case where there can be a deficit in masses, and that mass deficit is equivalent to an energy, and the energy is related to the mass deficit by a factor of c squared. It's another derivation of the famous Einstein relation that E is equal to mc squared. It's the conversion of mass to energy. Okay, when we make the composite particle, some of the mass is lost, and it shows up in this particular case as heat. Okay, and you should recognize this, of course, as the source of fusion energy, right? Conversion of mass to energy. So in summary, where are we? We've identified the relativistic momentum. We have a formula for it. P is equal to gamma times mv, and we have a formula for the relativistic energy. The relativistic energy is gamma times mc squared. Okay? And we've learned that both of those quantities are conserved. Okay? And they replace the Newton's ideas of conservation, which was that his momentum was conserved and that his masses were immutable. Okay, masses are not immutable anymore, but there is a conservation law that replaces them, and that's the conservation of relativistic energy, which is gamma times mc squared. In all these formulas, when I write m like this, it's just the rest mass of the particle. And I've made explicit all of the velocity dependence elsewhere. All four of these quantities are conserved. Okay. So one of our challenges is going to be to understand this conservation of four quantities in a more fundamental fashion, and that's what we'll be turning to later in this